Let us try this example from quiz 6A question number 1. A periodic function f is defined by this function, where fx is equals to 0 when the interval between negative pi and 0, and fx is equals to 1 when the interval is between 0 and pi. So this is a function periodic with period of 2 pi. Okay, what you need to do is you have to sketch the graph of the function over the interval negative 3 pi to 3 pi, and then you find the Fourier coefficients corresponding to the function, and the last one is you have to determine the corresponding Fourier series. For question A, you have to sketch the graph of the function over the interval negative 3 pi and 3 pi. So this is the axis for fx, and this is the axis for x. Okay, since the function is periodic, so we only need to sketch it over one period. So meaning that we have to sketch it for the fundamental interval, which is based on the question is from negative pi to pi. So the value of negative pi at x until pi. So we know that for negative pi to 0, the function is equals to 0. So we can draw it like this. Okay. And then from 0 up to pi, the function is equals to 1. So let's say 1 is somewhere here. So up until pi, the function is like this. Okay, then we can repeat the pattern from negative 3 pi to 3 pi. So meaning that we have to draw up until 3 pi, and this one is from negative 3 pi. Okay, so it is repeated, meaning that for the first period is at 0, and the second one is at 1. From negative 2 pi to pi is 1, and from pi to 2 pi is 0, and from 2 pi to 3 pi is 1. Okay, so now we have already sketched the graph from negative 3 pi and 3 pi. Okay, next you need to find the Fourier coefficients corresponding to the function. What is Fourier coefficients? Fourier coefficients is, if you remember this equation where fx is equals to 1 over 2 a naught plus the summation of an cos n pi x over L plus b sub n sine n pi x over L, where n is start from 1 up until infinity. So the Fourier coefficient is this a naught, a sub n, and b sub n. So we need to find the value of a naught, and then the value of an, and the value of bn, where a naught is given by 1 over L, the integration of negative L to L, fx dx. Okay, first we try to solve a naught. So this is, we know that L is equals to, the period is equals to 2 pi, where this is equals to 2L. So L will be equals to pi. So 1 over pi from negative pi to pi, where fx is the function of fx dx. Okay, we rewrite this, but the function here The interval is start from negative pi to 0, and the second function is 0 up to pi. So we have to separate this. So we start from negative pi to 0, where the function is equals to 0. And then the second interval is from 0 up to pi, and the function is equals to 1. So now we can solve this integration, where this will be equals to 0 and the remaining will be 1. So the integration of 1 will be x, where the interval is from 0 up to pi. Then substituting the interval with x, so we get pi minus 0. So the value of a naught is equals to 1. Okay, now we proceed with an. So an is equals to 1 over L, the integration from negative L to L, fx cos n pi x over L dx, where n is equals to 1, 2, 3, and so on. Okay, now we substitute all the values, where L is equals to pi. So the integration is from negative pi to pi, fx cos n pi x over pi dx. Okay, now we know that the fx value is different for different interval. So we start our integration from negative pi to 0, because it is from negative pi to 0. So the function of fx is equals to 0 times this is equals to 0. And then the second integration will be from 0 up to pi, where fx is equals to 1 times cos n pi x over pi is equals to nx dx. So 1 over pi, this will be 0, and the integration of cos will be sine of nx divided by n, where the limit is from 0 up to pi. Then this will be 1 over pi sine x is equals to pi over n minus sine 0 over n. Okay, we know that for every pi, the value will be always equals to 0, and sine 0 is equals to 0. So 1 over pi times 0 is equals to 0. We have obtained the coefficient for a naught and an. So now we proceed with the coefficients of b sub n. Okay, given the formula for b sub n is 1 over L times the integration of fx sine n pi x over L dx. Okay, next we substitute L with pi, negative pi to pi fx sine n pi x over pi of dx. Okay, we know the function of fx, given that it is from negative pi to 0 and 0 to pi. So first we do the first interval, where from it is from negative pi to 0, where the function from negative pi to 0 is equals to 0. And then the next one will be from 0 up to pi, and the function is equals to 1 times sine n x dx. So now we can solve this where it will be negative of cos of nx, and then we differentiate this will be over n from 0 up to pi. So this can be written as substituting this x with pi and 0, so we get cos n pi over n minus n negative will be positive cos 0 over n. So this will be equals to 1 over pi. Okay, this is the most important part, cos n pi. We know that for cos, the graph of cos is something like this, where this will be pi and this is 2 pi, 3 pi, this one is 4 pi, and so on. So if you notice that the value of n pi, where n is equals to odd number 1, 3, 5 up until odd number, the value of n pi is equals to negative 1. And when n pi is even number, for 2, 4, 6 and so on, 2, 4, 6 and so on, the value of cos will be 1, equals to 1. So we can write this where this bn is equals to 1 over pi, where negative of, so we can write it as negative 1 to the power of n over n plus cos 0 is equals to 1 over n. Okay, this can be simplified with negative 1 to the power of n. Okay, so now we take out n to outside, so we get 1 over n pi negative 1 to the power of n plus 1. Or we rewrite this as 1 over n pi 1 minus negative 1 to the power of n. Okay, so we can simplify this. We know that for for n for odd will result in different answer, and when n is even, it will create another answer. So first, for n equals to 1, 3, 5, the odd number, so this will be 1 over n pi 1 minus, where for odd the value of cos will be always negative 1. And then when n is even number, it will be 1 minus, so this always be equals to 1. So we rewrite this, we will get this, it will be plus, so 2 over n pi, where n is odd number, and it is equals to 0 when n is even number. So this is the equation, this is the value for coefficient b sub n. Okay, now for the next question is we want to determine the corresponding Fourier series. So from the previous equation, we already get the coefficient of the Fourier, where a0 is equals to 1, an equals to 0, and bn is equals to this. So we can substitute this coefficient into the Fourier series. Okay, substituting all these coefficients, we will get A naught is equals to 1 over 2 plus the summation of where an is equals to 0, so this will be equals to 0, and then b of n sine n pi x over L, where L is equals to pi. So this will be sine of nx, where n is from 1 up until infinity. So the next step is you expand this summation, where you get 1 over 2 plus, so the n start with equals to 1, so it will be b1 sine of x plus b2 sine 2x plus b3 sine 3x plus b4 and then b5 and so on. Okay, the next step is substitute the value of b1 into this equation. So b1 is equals to, when n equals to 1, the function will be 2 over n pi, where n is equals to 1, so we get b1 is 2 over pi times sine x. The next one is b2, when b2 is equals to 0, plus b3 will be 2 over 3 pi sine 3x, and then b4 will be equals to 0 plus 2 over 5 pi sine 5x and so on. And if you notice here, this is a sequence of 1, 3, 5. Okay, so from here, this is also the sequence of 1, 3, and 5. So our aim is to get the formula of the nth term from the sequence. So we know that this is the sequence of 1, 3, 5. So we want to find the sequence, the formula of the nth term, where this will be equals to a1 plus n minus 1d, where a1 is equals to 1 plus n minus 1 and d is equals to the difference between the two numbers, which is equals to 2. So when we expand this, we get the n term will be 2n and then minus 2 minus 1. So this progression can be written as 2n minus 1, can be presented in 2n minus 1. So we rewrite this for this case, where so this will remain as 1 over 2 plus, so we rewrite it back into the summation, where it starts from n equals to 1 up to infinity, 2 over pi, we take out 2 over pi outside, and then it will be sine. So this sequence now is become 2n minus 1 times x over 2n minus 1. So if you expand this, you will get the same series like this. Okay, so we simplify this, will becomes, we take out 2 over pi out, so we get summation of n equals to 1 up to infinity sine 2n minus 1 x over 2n minus 1. So this is the formula series for the function in question number 1. Okay, now I'm going to show you how Fourier series can represent a function. given this is the function of the previous example, and then we expand this function to be like this. Okay, so from here we know that we can create a partial sum based on this function, where the first partial is equals to first partial sum is equals to the first term, the summation of the first term, which is equals to half, and for the second partial sum, which is equals to the summation of first second term, which will be half, and second term will be 2 over pi sine x, and the third partial sum is equals to half plus 2 over pi sine x, and the third term will be sine 3x over 3. And let's say for up until fifth partial sum, it will be up until sine 7x over 5. So this partial sum, if you represent it as a graph, so for S1, this will be a straight line where the line is at equals to half. And when we increase the number of terms, finally we get the shape of this function. And then this is the graph for the third partial sum, and this is the shape of the third partial sum. Okay, you can see that as we increase the number of terms, the graph will approach to the shape of the graph of fx of this function. So the partial sum will converge to fx over the fundamental interval, or other words, we can say that the Fourier series can represent the non-trigonometric function. Okay, because as you know, this is a predicted function of fx equals to 0 from pi to 0, and 1 is from 0 up to pi. So from here we can get the Fourier series of this function, and we can say that Fourier series can also represent the non-trigonometric function.